Hello, class. This is Mr. Bean. This is going to be video lecture number 8, Inclined Planes for AP Physics. This is Unit 2, Section 3, or Unit 2.3 Dynamics. In this discussion, or this video lecture, we're going to discuss working with inclined planes. Now, last time we met in class, we dealt with the elevator type problems. Now, this is the next major section in dealing with dynamics is called inclined plane problems. Now here, I'll let you do some reading. There's a handout that goes with this, and we'll let you look at it, at your own convenience. But let's go and take a look here about the inclined plane, about what it is that we need to look at. So let's go ahead and kind of draw an inclined plane here, and we're going to use black here. So we'll go ahead and draw an inclined plane like right here. Let's go ahead and draw an arrow down, and it's much like a triangle, and we'll kind of go like this here, kind of inclined plane. Okay, so here's an inclined plane, and let's identify certain aspects of it. So right here, we'll call this here the angle theta. Okay. This is 90 degrees. Okay. And this angle here, we'll go ahead. I'm going to draw a double angle symbol here. This is going to be 90 minus theta. Okay. 90 minus theta. Okay. 90 minus theta here, because the interior angles of a triangle in flat Euclidean geometry must equal 180 degrees. So this is 90 minus theta. In fact, let me go ahead and write it out here a little bit better. 90 minus theta. All right, so let's suppose we have a block, okay, a block here, and we're going to assume there's no friction. Here's a block here, and it's resting on this inclined plane here, and we're going to say there's no friction. That will come later. No friction. So let's go ahead and kind of write that down here. No friction, and there we go, no friction. Now, this is going to be sliding down the inclined plane. So what we got here is that this is our coordinate plane system here. We can draw it like this. This will be the y component, and this will be the x component, like so. It kind of matches the incline here. So in this case here, since we're going down the plane, we'll call going down the plane to be positive. So going down the plane is going to be positive. Okay, so down the plane is positive. All right, so let's take a look here, and right here, this contact point, we're going to assume all the forces are acting on this point right here. So what we got here is we have this. We're assume all the forces in our analysis are going to be concentrated right here. So let's go ahead and kind of draw a vector going straight down, and we'll call this vector here the force of gravity. So this would be the force of gravity vector. And we'll go ahead and put in a G here. And from last class, we know that force of gravity is going to equal mg, acting straight down. Okay, now we have some components of this. Let's go ahead and kind of draw, I'll use different colors here. There's components of this vector. So there's a component right here. Well, this component here is the perpendicular component. Perpendicular. And we'll go ahead and write it like this here. This is the perpendicular component because it is perpendicular to the plane here, to this inclined plane. Then we have another component here. This component here is going to be the parallel component. It is parallel to the inclined plane. And we'll go here, parallel component, like that. There we go. So we have the perpendicular component, and I have the parallel component. Now this green component here should be parallel with the inclined plane. It's not quite, but it's, it should be. All right, so looking at it here, we can see that this is clearly at 90 degrees. What I must show you is that I must show you that this angle right here, this angle here is also the same as this angle here, theta. Okay, I need to show you that. All right, so let's go ahead and see how I can show you that. Let me go ahead and use a different, I'll use this blue one here. And to start off, let's go ahead and just draw, I'm going to extend this line this way. And this line right here, this vector, I'm going to go ahead and extend the line like so. Okay. Okay. So we should have two parallel lines. We'll kind of go like this, and we'll kind of go down, and we'll kind of go down like this here. All right. So we have two parallel lines. Now from geometry class, we know that if we have a transverse cutting through two parallel lines, there's some relationships. So here we have alternate interior angles. We'll go ahead and kind of draw this like this here. And this angle is equal to this angle here because alternate interior angles. This angle and this angle here are also the same because they're vertical angles. Okay, they're vertical angles. Okay, so you're with me so far? Alternate interior, vertical angles. Now take a look at this angle right here. Okay, so we're looking right here. Remember, this is the perpendicular component. So this entire angle right here is 90 degrees. This whole thing here is 90 degrees. So if this is 90 minus theta, it means that this angle right here must be theta. Must be theta. So that's theta. Okay. All right. Now, we don't want to keep doing this every time we see an inclined plane. This is just something that we just need to know. Now, if this is truly, if this is the theta here, then there's certain relationships that unfold. Now, I'm going to go ahead and put my little guy here, Jack. Okay, make sure you know Jack. He's going to help us out here. Jack, this is Jack's perspective here. Okay, let me go ahead and go over here, and I'm going to use red here. So this component here, this is the cosine. Okay, so this is mg. So this here, the perpendicular component, is going to be mg, right? mg cosine of theta. Let's go ahead and write down here cosine of theta. It's kind of tight in. It's cosine of theta. So if this is the cosine, that means that this here is the sine. So I'm going to go ahead and use a green pin here. So this here, the parallel component is going to equal mg sine of theta. mg sine of theta, like so. mg sine of theta. Now, because we learned from vectors that you can move them around in space, as long as you keep the same orientation and magnitude, I can move this vector up here, like so. So this vector is going down like this here, and it should be straight down the line here. So this is the parallel component, and it's going to equal mg, right, sine of theta. So this, we have to know this. Okay, you have to memorize this. The parallel component, or the force, or what's causing this block to slide down the ramp, is the parallel component of gravity, which equals mg sine of theta. Okay, now likewise, this is the parallel component. Okay, and now let me go ahead and use this pin here. So this is the perpendicular component right here. Now, this is the normal force going up this way. This is the normal force. Okay, the normal force. So, okay, so right now, the only two forces that are acting on this block here is the force of gravity and the normal force. These are the only two forces acting right now. We've excluded friction. So these are components. These are components. They're not the actual force vectors. Okay, so we have to make sure we distinguish that. So going forward now, when asked a question, this is the parallel component of gravity, mg sine of theta, which causes or is responsible for the block to slide down the ramp. Okay, all right. So let's look at some potential problems here, and we'll let you do some of these, and I'll do some as an example here. Here we have some answers here. Okay, so let's go ahead and change this to black here. It says, suppose a cart in figure 5.1 has a mass of 1 kilogram and an angle of 30 degrees. What are the forces of, on the ramp along along forces are on the cart along and normal to the ramp. So figure 5.1 is way back here. Well, this is figure 5.1 here. So 5.1. This is figure 5.1. All right, so we'll go back over here and we'll just kind of, it's helpful to sometimes just draw a little triangle here like so. our ramp. Okay, it's kind of steep here, and we'll kind of go like this here. Here it is. And so it says here that this angle here is 30 degrees. So we're going to put down 30 degrees here. Okay, 30 degrees. Okay. And so we want to know along the ramp is the parallel component. That's along. There's the parallel component. Okay. And it says here the normal. Normal to the ramp means 90 degrees or perpendicular. Perpendicular. Okay. Uh, in college here, I took Calc 1, Calc 2, Calc 3, and differential equations until I figured out that normal meant perpendicular. Okay, so I want to make sure we have this down. All right, so what we know then is that this is going to equal mg, right? Uh, uh, cosine of theta. Okay, mg cosine of theta. Okay, we just have to know this. Okay, because you can't keep looking it up on a textbook or on an equation sheet. You just have to know it. This is going to be mg sine of theta here. Mg sine of theta. Okay, so using our calculator here, so we plug in, so mass is 1 kilogram. So 1 kilogram times 9.8 times a cosine of 30 degrees. So we'll go ahead and kind of use a calculator here. And so I'm going to plug in the values. So this should equal, we'll go ahead and put in here 1 times 9.8. Times the cosine of 30 degrees gives us 8.48, okay, which will round to, we'll say 8.5, which is our answer here. And this is going to be the parallel component, which is mg sine of theta. So 1 times 9.8 times the sine of 30 degrees is going to be 4.9. This is 4.9. And so you can pause the video here or hit pause because you guys are going to answer questions 2, 3, and 4. Okay. Next section here. We're going to talk about acceleration and inclined planes. Okay, again, here's some reading here. Here's a worked example. Let's go ahead and kind of see what's going on here now. Okay, so it says here, suppose a block of ice is on a ramp with an angle of 60 degrees. What's its acceleration? Okay, all right, so let's go ahead and kind of draw a picture and just kind of see what we're looking at here. Okay, just kind of see what's going on here. So here we have this block of ice. Okay, so that assumes it's frictionless. Okay, there's no friction, and this angle here is given to us as let's say 60 degrees. Okay, 60 degrees. Okay, good. And what's the acceleration? Okay, now, oh, where's the mass? You know, oh, Mr. Bean, mass is not given. Well, let's hold on and let's see if we need the mass. Okay, let's take a look here. So we'll go to Newton's second law. Sum of the forces, right, is equal to ma. Okay, now, so here we have the force acting here. Here we have, this is the parallel force right here, right? Parallel force. And we also have a normal force acting like this. Okay, normal force. All right. So the assumption, remember now, so when we look at this here, remember now, this is the X component and this is the Y. So we'll get into two-dimension vectors later on, but we don't need to do it right now. So we only, since this no friction, we only care about the parallel force here. So this is the only thing we're worried about is the parallel force or the component of parallel force. So in here, then I would substitute in the parallel component right here. So it's going to be, we'll call it in the X direction. Okay. And this is accelerating in the X direction, just to be precise. Okay. Equals, right? And this is going to be M here, and this will be AX. Okay. Now, what is the parallel force? It is mg, right? Sine of theta. And we'll go here, sine of theta. And this is going to equal m ax, like so. All right, there we go. Now we can see that the masses cancel out. Okay, so if you don't see mass, we don't need to get freaked out because it may cancel out later. So this ends up being g right here, sine of theta. And this should look very familiar to a lab we did in class, where we're trying to measure g by using the ramp, right? All right, so we would go ahead and put in here 9.8, like so. Okay, and we will say sine of, what we got here? Sine of 60 degrees. Okay, sine of 60, okay, equals acceleration. And so if I take 9.8 times the sine of 60 degrees, I get 8 point, so the acceleration is going to be 8.49 meters per second squared, like so. Okay. So, good example here. So we'll let you guys do 6, 7, and 8 on some follow-up questions. So the video, you can pause the video here to look at this, write this down, and then answer the next several questions. The next section here is going to be running down ramps, speed. Okay, speed down a ramp. So suppose we want to find the speed going down a ramp. So again, here's an example up here. Now notice here in this equation, they have s instead of x. Sometimes some teachers or some textbooks will use s instead of x to show distance, but we should be versatile. Okay, so here's this one here. I think we're almost done here. Yeah, this is the last one here. It says starting from rest, you go down a 100-meter ski jump of 60 degrees. What is your speed at takeoff? So here we have like a kind of a ramp like this here, and maybe here's a cliff, and so here's a skier coming down the this ramp here, or this ski ramp here, and this is here's the angle theta right here, and he's going to come down the ramp here and then go off like this. So that's what's happening here. Okay, here's the picture here, and they want to know what's the speed. Okay, not velocity, speed. So it's a magnitude we're looking for, and this is 60 degrees. Okay, again, no mass is given, right? Mass is not given, so we don't need to worry about it right now. Okay. So first thing we need to do, so speed. So there's no time. Look at, there's no time given anywhere. So that means that we have to use v squared, right? Plus, now our reference, okay, here it is. This is x, and let's make it x a little bit better. And this is y here, okay? Going down the ramp is positive, Okay, make sure we have that down. So this is v squared. I don't want plus here, so I'm getting an eraser. Let's get rid of that there. Okay, and let's go back to right here. Okay, all right, get rid of this, and we'll kind of there we go. So v squared, right, is equal to VO squared, right, plus 2a, and here we'll have delta x. Okay, so we should be familiar with this equation now. So we're looking for the what's the speed at takeoff. Now they don't. It says start from rest, so we know that VO is going to equal 0, which helps us out. Okay, so here is v squared equals 0 plus 2a delta x. So the only thing we need to know in order to solve this problem here is that I need to know what A is, because it tells us you go down a ramp ski of 100 meters. So that's going to be our delta x here. There's our delta x. Okay, so I need to find acceleration. So over here, we know this is the parallel component. Okay, now I'll do this all the way through, just so for to be precise and for extreme detail. Okay, this is MA, right? And this is going to be the parallel component that we're looking at, and that's going to be MA. So this is going to be mg, right? Sine of theta, okay, to be complete, equals MA. So the m's cancel out like so. So we have here g sine of theta is equal to a, like so. So the acceleration now is going to be we'll use 9.8. Now you could use 10, that's fine, but we want here sine of, was it 60 degrees, right? So sine of 60 degrees. Okay, and the acceleration should equal, let's see what we got. I have here 9.8 times the sine of 60, which should be 8 point, we'll say 8.5. We'll go around to nearest tenth. 8.5 meters per second squared. Now it's pretty, again, the no friction. There's no friction, so it's close to 9.8. But you're accelerating pretty fast. So here we'll go. Here's velocity squared equals. So we're going to have your 2 times 8.5, right? 2 times 8.5, close parenthesis, and times it by 100. And we need to negotiate this problem here. So velocity should equal, so let me go ahead and get my calculator, do it in one step. It's going to be 2 times 8.5 times 100, closed parenthesis, and 41.2. So we have here 41.2 meters per second is our takeoff speed. All right. We'll leave the rest of there'll be 3 more questions to follow for you to practice, and that will conclude lecture number 8.